Welcome to our first official lecture video about modern physics. This time around, we will be studying the history of the development of modern physics. We can say that in a picture, the development of modern physics can be captured by the ideas contributed by these scientists. Mainly, we have Aristotle, Isaac Newton, and then Albert Einstein. The ancient Greeks held the record of a systematic effort of studying motion. Aristotle studied natural philosophy based on the assumption that every substance in the universe has a proper place, and that motion occurs because a substance tries to achieve its proper place. With this, time was given a similar absolute meaning that it is moving to achieve some end goal. For 2000 years, this Aristotelian physics was embraced. The latter part of that year, an Italian scientist in the name of Galileo Galilei established the importance of experiments, which disintegrates the concept of Aristotelian physics. It was in his famous Leaning Tower Pisa experiments that debunked the concept that heavier object moves faster than lighter object. 100 years later, Isaac Newton generalized the results of Galileo's experiments. With this, he successfully established the three laws of motion. It was in this time that the Aristotelian physics was completely abolished. Multitude of major discoveries and physical theories have been developed in the next succeeding 200 years. Most of the latter failed the sophisticated experimental tests. Newton's theories had been joined by equally impressive laws of electromagnetism and thermodynamics, made possible by James Clerk Maxwell and Sadi Carnot in the dawn of 20th century. This remarkable event made the scientific community believe that the description of the physical universe was complete. Albert Michelson even said at the end of the 19th century that the grand underlying principles have been firmly established. The future truths of physics are to be looked for in the sixth place of decimals. Such optimism turned out to be premature, as there was vexing cracks in the foundation of Newtonian physics. The two cracks were mentioned by Lord Kelvin in his famous Baltimore lecture in the 1900s. These were the blackbody radiation and the famous Michelson-Morley experiment. Now, in the blackbody radiation, the object absorbs all radiation incident upon it and re-radiates energy, which is characteristics of this radiating system, and not dependent on the type of radiation which is incident upon it. The radiated energy can be considered to be produced by resonant modes of the radiating object. The classical thermodynamics predicts that as the wavelength of this distribution decreases, the temperature increases. Unfortunately, this was not the case as observed here. The temperature drops out when the wavelength decreases. For the case of the Michelson-Morley experiment, the experiment compared the speed of light in perpendicular directions in an attempt to detect the relative motion of matter through the stationary luminiferous ether, and the result was negative. That means there was no significant difference between the speed of light in the direction of movement through the presumed ether and the speed at the right angles. The development of the theories of quantum mechanics and general relativity dispelled the cracks of Newtonian physics and gave answers to various puzzling phenomena. The application of these theories to microscopic systems such as atoms, molecules, fundamental particles, and to macroscopic systems of solids, liquids, gases, and plasmas has given a deep understanding of the intricate workings of nature and has revolutionized our way of life. That's where modern physics born. Thank you for listening, and I hope to see you soon in our next video, which will talk about relativity.